Greetings. Welcome to my video lecture on some more examples on chi-square goodness of fit test. Here we'll be looking at number 7 from the worksheet. According to a scientist's claim, 30% of self-pollination produces red, 40% pink, 30% white flowers in a particular plant. So obviously my claim here is that the first P is 30%, so P1 is 30% and P2 is 40% and P3 is 30%, and we all know this is my null hypothesis. 230 observations. These are my O's, so that's my O1, sorry, Q, that's my O1, that's my O2, and that's my O3. And it says use a 0.05 significance level to test the claim. Alright, so goodness of fit test, we're trying to see if these P's are indeed the way they're expected to be. So my status quo or null hypothesis is that P1 is 30%, P2 is 40%, and P3 is 30%. And my alternative hypothesis, as always, is at least one is different, alloyed. And this is my step number 1. Whoa, that went haywire. So this is my step number 1. Alright, my second step, as you've seen before, is to calculate the test statistics. My test statistics here is chi-square is equal to the sum of O's minus E's quantity squared divided by E's. Of course, I have my O's here. I can calculate my E's, and remember that the first E is first P times the sum of the observed frequencies. My second E is second P, and when I say first P, second P, I'm talking about first P from the null hypothesis from here. Second P is from here. So my first P is 0.3, my second P is 0.4, my third P is 0.3. So my third E will be P3 times the sum of the O's. Of course, I have to show you this on a spreadsheet, and the second step is purely a spreadsheet, so I need to go in, unless I want to write this the way we did it before, where you just use pencil and paper and you draw columns and you write your O's 55, 110, and 65. And then you could, and then you add them all, because you kind of need to know the total. So 230, that's the total. So doing it without Excel, this is what you do. So you write them all out, and then you calculate your E's. What's my first E? My first E is my first P, which is 0.3 times the total O, which is 230. My second E will be 0.4 times 230. And then it'll be 0.3 times 230 again. And hopefully if you add them up, you get 230, because remember these two sums, the sum of the O's and the sum of the E's must be equal to each other, so you know you haven't made a mistake. So now, once you have that, then you can calculate your test statistics, which will be O, which is 55, minus E, which is whatever this is, quantity squared divided by E itself. And then we just drag that down. But right now you don't need to do that. I'm going to show you how to do all that on a spreadsheet as I did before. So we'll just move on to our spreadsheet and take it from there. So let me switch screens so you can see how this is done on Excel. Let me bring this up, and I've outlined it here for you. So it's number 7. And let's see. So my H1, my HO is P1.3, P2.4, P3.3. I need those so I can calculate my expected frequencies. I've already entered my O's. So let's calculate my first E. Again, my first E is 0.3, which is the first P, and I have it written here, where you see E1 is the first expected frequency is calculated by multiplying the first P by 230. So my first E is going to be 0.3 times 230. My second E will be 0.4 times 230, and my third E will be 0.3 times 230. And again, as I said, we always want to add them up to make sure that the sum of O and E are the same, and thank God they are. So we've calculated our E's correctly. Now I can calculate my test statistics, which is O minus E, quantity squared divided by E. I drag that down, and then I sum them to calculate the test statistics. Let's sum it. There we go. So my test statistics is 6.59. So my test statistics is just that. I guess that was it. There we go. Sorry. My test statistics is that. And I can round it to as many decimal places as I like. So my step 2 for my hypothesis testing procedure here for number 7 is 6.594. Or 6.59 or 6.6 or however number of decimal places you've been instructed to do so. I mean, if nobody tells me anything, I'll just leave it as 6.594. I mean, 3 decimal places makes you pretty accurate, and you can't get any more accurate than that. Alright, so let's go back to our calculation. So now I know what my step 2 is that I calculated on Excel. So my test statistics is, I could erase the formula. My test statistics is 6.594, and there's my second step. Now my third step, which is the drawing step, which is the step in which you find the rejection region, as you recall in this module for the goodness of fit test, will be a chi-square distribution, which is skewed, starts at 0, and recall it's always going to be a, that's right, right tail test. And as always, let me shade it in. That's my rejection region. Trying to do a good job shading this thing. So there we go. Excellent. And my alpha is what does it say? 0.05. So my alpha is 0.05. My rejection region is 0.05, the area of the rejection region. That's what alpha is. It's always a right tail, and remember that's 0, and this is a chi-square distribution. Now what is my critical value? What's my gatekeeper? Now here it's a chi-square inverse right tail 0.05 comma k minus 1 degrees of freedom. So it's equal to, and I'll just write it, chi-square dot inverse dot right tail alpha and degrees of freedom. Alpha is 0.05, and degrees of freedom is number of categories minus 1. So 3 categories here, so 3 minus 1 is 2. So that's going to be the command I need to use to calculate this critical value here, the gatekeeper. So let me just do that on a spreadsheet for you guys so you can actually see it done. Let's come here again. Alpha is 0.05 here. Alpha is 0.05, k category is 3. So my critical value, CB, they usually label it as, is chi-square inverse right tail. My probability is 0.05, that's alpha. My degrees of freedom is k minus 1, 3 minus 1, which is 2. And the answer is 5.991. And that's my critical value. So let me move back. Gatekeeper, that's where the rejection region starts from. So 5.991. Very good. So now I have a value here to use for the gatekeepers, 5.991. Very good. And that is my step 3. Alright, now my step 4 will be the decision and conclusion. Decision is pretty standard. The test statistics here is 6.594. That falls in the rejection region because obviously 6 is greater than 5. And therefore our decision will be to reject the null hypotheses. Since you're rejecting the null hypothesis, you're saying that these probabilities that you see here are not the way you thought they were. So therefore you say probabilities are not distributed as was expected. And that'll be the conclusion for a goodness of fit test. And there's our 4 steps: our null and alternative, our test statistics, our rejection region, our decision, and conclusion. Thank you.